is Gisela, and I'm a postdoc with Olaf Wiest. And today I'm going to talk about how we use UMA in our lab. And so, whoops, a little bit of introduction. If you haven't heard what UMA is, UMA stands for a family of universal models for atoms. This is a tool that was developed by FAIR at Meta and also the Department of Chemical Engineering at Carnegie Mellon University. And so this tool was released this year over the summer, and it's a graph neural network. It has sort of the same architecture of messaging passaging, very similar to IMeNet 2. But this tool has been trained on 500 million structures, and they claim that you can study any reaction, look into their ground state structures, their transition structures, very well with neutral molecules. You can try some charge in radical molecules, but it's not fully accurate. But you can try it and see how the results look like. And they claim if you wanted to look into sort of the speeds and how it does, you can do MD simulations of 1,000 atoms at 1.4 nanoseconds per day for on a single 80 gigabyte GPU system. So before UMA was released, actually earlier this year, Meta released Open Molecules 2025, or also known OMOL 25. So this is a large molecular data set that covers biomolecules, metal complexes, and electrolytes. And so it was trained on 100 million DFT molecules at fairly high level of DFT theory. And it's 83 elements of up to 350 atoms. So it's a very comprehensive chemical space coverage and data set. So together with this data set of OMOL 25, along with 4 other additional data sets, this was all implemented and gathered together into what is now known as the UMA. So you can look into molecules, small molecules, materials, crystals, and MOFs. But specifically in our group, since we work with small molecules, we are interested in the OMOL 25 database data set that is implemented into UMA. But overall, as I mentioned before, it's a 50 million trained platform. It has a novel mixture of linear experts architecture, which basically has 1.4 billion parameters with about 50 million that are active. So it increases its capacity and efficient scaling without sacrificing its speed. So essentially, it has provided these 4 or 5 different data sets for the UMA models, and you get this sort of consumed platform that uses all these data sets to have sort of a chemical understanding of how chemical interactions occur in chemistry. And so that was a little bit of a brief background of what UMA is. And now moving on into more sort of the tutorial session. Before you can actually run UMA, there are a few things that you need to sort of set up and install. So if you're new to coding and UMA and MLIPs, you probably have to start from getting accounts from GitHub and Hugging Face. So then once you have an account with Hugging Face, you log in and you submit a request to download the UMA model weights. So you can go to Hugging Face Facebook UMA website. So basically you just submit your request to download those weights. It's basically a way for them to verify that you are a real person and to see who you are. And so within a few minutes, you get an email notification that you have been accepted to get the UMA model weights, and you just click on the download link to have those weights downloaded wherever you want them on your computer system. And then here at Notre Dame, we are strongly recommended to have a Conda environment whenever we run AI and machine learning tools for our research. It's just a safe environment to be able to run these. So this might or may not apply to you, but that's just what we have to do here in our CRC system. And then along with having an account with GitHub, you want to clone the UMA repository, also called FairChem. So you can go to their link here, github.com, Facebook Research FairChem. And there's sort of 2 forms to install download all the folders and all the scripts from UMA. One way is to do this pip install Ferrochem core. This is basically if you just want to have those files without having to actually like edit the code or dive deep into the code. You just want to like use it and apply it. Just use pip install Ferrochem core. But there is another pip install command if you want to like have a little bit more access into the code and like change it specifically a little bit more to whatever research or task that you want to do. So then in order to run the UMA models, you need to have access to the AEC Ferrochem calculator. The Ferrochem calculator is provided by UMA, but it uses AEC, which is Atom Simulations Environment. And so then what we have done is we call on that Ferrochem calculator scripted through a Python script to do certain tasks. And what we wanted to do is do geometry optimization. We wanted to do nudge elastic band or NAB, as well as transition state optimization and IRC scans, we also use Cella, which is an open source automation molecular saddle point optimization, so specifically for transition state structures. And then the final task that we wanted to implement was energy calculations. And so with the help of Nicholas Cassetti from MIT, he helped us to write this scripted Python script we call Ferrochem calculation. So it's just a way to automate these different tasks and call on the Ferrochem calculator to use the UMA weights and the models. So here's a sort of a screenshot of what our Python script looks like in the core. So you can see that we have a place to input our XYZ input coordinates, our output XYZ file, our calculation type. We can call on geometry optimization, NEB, TS optimization, IR, or energy. We have to tell it where the actual UMA models are in our directory. So that would be here. The task name. So again, as I mentioned before, since we are small molecules, we want to use OMAL 25, but you have access to the other data sets that are also available with UMA. And then here at the bottom, you can see that we have the calc equals Ferrochem calculator. So this is where we call on that Ferrochem calculator through this script. So then going into the sort of the overview of our terminal of like what you should have these sort of things. You should have your Ferrochem folder, which is where we have cloned the UMA repository from GitHub. We have the Ferrochem calculation Python script, which is self-scripted. You can create your own. And then we have UMA folder where we actually downloaded the UMA model weights from Hugging Face. And when we also have our submission job script. So here at the CRC Notre Dame, we have to submit jobs through a bash file. So that's what we have here. And then last of all, we have like our molecules that you can have in XYZ files, or you can have in other sort of input files that can be implemented with UMA. And so that's just like an overview of what you should have on your terminal. And now you're ready for calculations. So here I'm going to show an example of how we use UMA for an elementary step for palladium catalyzed oxidative addition. So we have our catalyst on the left. We have our product from the oxidative addition TS, our substrate coming in, and our TS structure. So in order to analyze these, we might start with the catalyst and do a geometry optimization. So in our submission job script, we activate our conda environment. We run our Python Ferrochem calculation script. We tell it that I want it to look into the catalyst XYZ file. The output should be a catalyst output XYZ file. And that calculation type is a geometry optimization, which I highlighted here in orange. And then finally, I tell it where the UMA models are located in my directory. So if you were to run this, on a CPU system, this would take about 28 minutes, but it's more recommended to run this on a GPU system. So that would take about 49 seconds to do a geometry optimization of the catalyst, and you get your final XYZ file. So once you have your output file, you want to do a quick energy calculation to get the actual energy right. So we just change our task in our submission job folder where the calculation type is now energy. And so if you were to run this on a GPU system, this would take about 14 seconds to run, and you get a final energy value of the electronic energy for that structure. So then moving on to the transition structure, you would do sort of the same thing as I've shown in the previous slides, where you now change the task that you want to do in your submission job. So we would do an NAB, for example. You can replace this with any other physics-based TS research, a search algorithm to find a good TS structure. Then you further optimize that TS, do an IRC to verify that that is a transition structure, and finally do an energy calculation. So when we run this with UMA, you would get this results in within seconds to minutes scale. And then finally, you can do the same geometry optimization and energy calculation to do the product. And then you do some simple math to just get the energy barrier for this transition structure. So that's sort of an overview of how we would use UMA. I also wanted to showcase another example that may or may not come up when you do like DFT optimizations or you want to do like a torsional scan. And so here's an example of just a very simple molecule of ethane, just for proof of concept kind of idea. So we all know that if you were to rotate ethane around that CC bond, you would get two conformations, the eclipse form and the staggered form. If you do this with DFT, it would be like minutes to hours scales. But if you were to imagine to run this with a larger molecule with DFT, this could take hours or days even to run this. But we wanted to see if can we do something like this with UMA, and we did do this with ethane, where we actually did 1 degree increments for a full 360 rotation, and this took about 16 minutes to run. And you can see we actually have really good energy results of 2.6 kcals per mole. And I just wanted to showcase like how you can use this tool. You can expand this more to like a larger molecule, do 1 degree increments, which you would never do in DFT, but you can do it with MLIPs because it's very fast. So finally, if you guys have any questions specifically to UMA, you can reference their papers, their models, their codes in GitHub, or directly send them an email to Facebook or Meta. But if you have questions for us here from Notre Dame or MIT, you can send us an email to myself or my colleague Mihir, as well as my colleague Nicholas Cassetti, who also helped with this coding and scripting. Thanks.